one of the interesting things that you'll see is that your titration curve is going to change shape depending on what your Ka is. So for a strong acid, the strong acid down here, it's got a very sharp sigmoidal curve. And as you get to a weaker Ka, smaller Ka, like 1 times 10 to the minus 4, something like acetic acid, it's going to shift this baseline up. So this buffer region here, right, is going to be higher, right, because pH equals pKa plus the log of AHA, so it's centered around the Ka. pKa, right, and go to an even weaker acid, it moves it up again and go weaker and weaker and weaker, right? And so this is basically a weak base instead of a weak acid because the Ka is below 1 times 10 to the minus 7, right? And so the smaller and smaller your Ka is, the smaller this what's called a titration break is. So this titration break is going to be very, very small for something that's got a small Ka. So for very weak acids, it might be really hard to figure out where this is. And we've got some tools that'll be in optional videos about how to find that. But just be aware that as I get weaker and weaker acids, I'm going to have different positions of this buffer zone, and it's going to be a smaller and smaller inflection in the curve here. As I change concentration, right, so if I've got the same acid, what's going to happen is where this happens on the x-axis is going to shift. So if I've got a less concentrated weak acid, it's going to move to the left. More concentrated weak acid, it's going to move to the right, but it'll keep the same basic shape. Let's look at a practice problem. So I've got 50 milliliters of 0.2 molar sodium hydroxide. This is a strong acid, strong base, titrated with 2 molar nitric acid. Calculate the pH after adding 30 milliliters of nitric acid and at the equivalence point. This one here should be easy cheese, right? At the equivalence point, because it's a strong acid and strong base, it's a pH 7. It's neutral. Weak acid and weak base, going to be different, right? So if it's a weak acid with a strong base, the pH would be above 7. This is a strong acid, strong base. Right? Figure out what it is after 30 milliliters of NaOH. Well, the first thing I need to do is figure out how many moles of NaOH I added with my 30 milliliters. And so I've got 50 milliliters of sodium hydroxide. I'm going to convert that into moles of sodium hydroxide, so 50 milliliters or 0.05 liters times the concentration of 0.2 moles per liter gives me 0.01 moles of sodium hydroxide. For the NH3 that I've added, it's going to be 0.03 liters, so it's 30 milliliters of 0.2 molar nitric acid, so 0.03 liters times 0.2 moles per liter, 0.006 moles of nitric acid. I do my chemistry stoichiometry step, where I start off with 0.01 moles of hydroxide, and I've got no acid, and then I'm going to add in my 0.006 moles of strong acid. It gets completely consumed. I've got no acid left, and I've got an excess of 0.004 moles of hydroxide. Take that 0.004 moles of hydroxide, divide by the total volume of 80 milliliters, or 0.08 liters. Figure out the hydroxide ion concentration is 0.05 molar. Take the minus base 10 log of that to get the POH, and then find the pH from there. And with a strong acid, the pH of 7 at the equivalence point. Okay. Let's look at one with a weak acid being titrated with a strong. So for my weak acid, I've got 40 milliliters of 0.1 molar nitric acid being, this is the titrant, this is the titrate, this is the weak acid, this is the strong base. What's the volume required to reach the equivalence point? We want to know what the pH is after adding 5 milliliters of titrant, and what's the pH at 1/2 of the equivalence point. Well, the first thing we're going to need to do is figure out that equivalence volume. So that's almost always one of the first things you want to do, is figure out the equivalence volume and the number of moles of your titrate. Right, so I've got my moles of HNO3. I need to figure that out. So I've got my volume of nitrous acid, 0.04 liters, times the concentration, 0.1 moles per liter. So 4 times 10 to the minus 3 moles. So I'm going to need 4 times 10 to the minus 3 moles of potassium hydroxide. I'm going to use the volume of, need to figure out that volume of KOH solution, so I've got the moles times the concentration to give me the volume. So 4 times 10 to the minus 3 moles times 1 mole for 1 liter for every 0.2 moles of hydroxide. So I need 0.02 liters of potassium hydroxide, or 20 milliliters of potassium hydroxide solution. You can kind of look at this and figure that out. Some books will actually say do M1V1 equals M2V2. Do not do that because your stoichiometry may not be 1-to-1. All right, don't do M1V1, M2V2. Do it this way with the moles. Sometimes, because this is a 1-to-1 stoichiometry, you might be able to look at that and go, well, this is twice as concentrated, right? My titrant is twice as concentrated. I'm going to need half the volume of titrant to equal the number of moles of titrate. You can kind of look at that. Sometimes see that. Don't count on it. Do it the right way, right? Once I figured out the equivalence volume, right, that's step 1. Now I can figure out the pH after adding 5 milliliters of KOH. This is one of those ones where I'm going to need to do the stoichiometry. So I figure out the number of moles of hydroxide ion I added in. So 5 times 10 to the minus 3 liters, that's 5 milliliters, times the concentration, 0.2 moles per liter, gives me 1 times 10 to the minus 3 moles of hydroxide that I added in. So before I added anything in, I had 4 times 10 to the minus 3 moles of nitrous acid. I added in 1 times 10 to the minus 3 moles of hydroxide. I've got more acid than I've got base. So I've got leftover weak acid, so 3 times 10 to the minus 3 moles of nitrous acid, and I've made 1 times 10 to the minus 3 moles of NO2 nitrite. Right. I've got a conjugate base, I've got a conjugate acid in solution. I'm going to use Henderson-Hasselbalch, pH equals pKa plus the log of the base over the acid. So 3.34 times is the pKa plus the log of 1 times 10 to the minus 3 over 3 times 10 to the minus 3. It gives me 3.34 minus 0.48, or 2.86. That's the pH when I've added in a little bit. So this is in my buffer region. At 1/2 the equivalence point, the moles are equal to the moles of conjugate acid, moles of conjugate base are equal. I've converted half of my weak acid into its conjugate weak base. So same number here, which means that I've got the log of 1. So pH equals pKa. So summarizing pH calculations during the weak acid with a strong base titration. At no milliliters added, it's just a weak acid solution. Use the acid dissociation, the equilibrium equation, ice table, and the Ka to calculate the H3O+. Between 0 and the equivalence point, it's a buffer. It's a mixture of HA and A-. Now, it's not always a buffer, right? So at the inflection points, like right where it's starting to curve, let's see these little curvy bits here at the beginning and here at the end, right? Not where it's reached the sharp incline and not at 0. So when I've got just a little bit of acid added, and here where I've got just a little bit of the conjugate base left, X is not small. It's only in this flat part that I can do it. But, go ahead, make a jump into the flat part. It's a buffer. Use the reaction stoichiometry to calculate the moles of HA, and A- after OH- converts into the HA into A-. You could, at any point between 0 and the equivalence point, always use an ice table. So ice table is always going to work. It's just that if you're in that buffering region where you've got a significant amount of both acid, conjugate base, then you can use Henderson-Hasselbalch. And in fact, you're going to make your life even easier and look at halfway to the equivalence point, pH equals pKa. Now, at the equivalence point, the only solute present is the salt. That's going to affect the pH. I've got some spectator ions floating around, like the Na from the sodium hydroxide. The anion minus, A minus, is the conjugate base of a weak acid. It's weakly basic. pH isn't going to be 7. It needs to be calculated. You calculate the molarity, the concentration of A minus from the moles that you started with, and the total volume. You can do an ice table for the base dissociation, obtaining Kb from Ka. You obtain the hydroxide ion concentration, and then convert to pH. All right, so it's a couple more steps. Beyond the equivalence point, it's just dominated by the OH-, the added hydroxide. The A minus, the conjugate weak base, is going to contribute a little bit to the pH. Right? It's going to make it a little bit basic, but it's going to be such a small contribution relative to the amount that's added by the OH minus that you put in. Use reaction stoichiometry to calculate the moles of excess OH, and then calculate the total volume, divide the moles by the volume to get the molarity of hydroxide, convert the OH to pH in 2 steps. Right? So here's a nice little table, or a nice little picture that does that. Right, so down here at point number 1, you're just going to use your strong, it's going to be your weak acid problem. Right, all along here in the flatty part, that's going to be your buffer, but you're going to pick this point here at 1/2 the equivalence volume. At the equivalence volume, you've got just your conjugate base in solution. You're going to treat it as a weak base. Between here and here, between 0 and here, I've got a mixture of both the conjugate acid and the conjugate base. Here I just have the conjugate acid. Along here, it's dominated by the excess OH. I still have the AC minus, or I've still got the A minus in here, but it's going to flatten out and you're going to use the excess. Go for an easy point. Go for 2 times the equivalence volume, right? So to summarize, right? Set it up as I've got this set up as a weak acid strong base problem. At 0 milliliters, H plus is going to be the square root of K times the initial concentration. At half the equivalence, pH is going to be equal to pKa. Right? I could Henderson-Hasselbalch all the way through the flat part, but why? Just do it at the halfway point, right? I could do an ice table all the way along here, right? But why? Right? Do it the easy way. At the equivalence volume, right? I know it's going to be basic, so I need to figure out a KB, because I just have my base in solution, conjugate weak base. Hydroxide ion concentration is going to be KB times the new volume, where the new volume is the moles of starting titrant. Right, so the moles of weak acid that I started with divided by the initial volume plus the equivalence volume. And then I go out to a 4th point, which is at 100%, or 2 times the equivalence volume. There, the moles of OH added are equal to the moles of starting titrant divided by the total volume. So the moles of OH will be the moles of weak acid that I started with, because I'm adding in twice as many hydroxide ion moles. Right? So the first equivalent went to neutralizing, and then the second equivalent is all just pure extra OHs. Right? I can do something similar, right, with a weak base as my titrate and a strong acid as my titrant. Right? Let's look at that real quick.